Okay, perfect.
Go ahead.
Okay, thank you, Ronan. Hello, everybody. I'm Ouala, postdoc here in IMT Atlantic, mainly working with Ronan, and I will talk to you today about learning the work we have been doing regarding learning numerical integration schemes for ODE, mainly for ODE integration and data-driven identification. Okay, so a quick overview of what we'll be going through, at least for this presentation. I will talk about, not necessarily introduce, but maybe present with our numerical integration schemes and present quick stability and precision criteria that are necessary to judge about the applicability or not of a given integration scheme for a given integration problem. I will then present some problematics with traditional state-of-the-art, and I will present, and I will then move to presenting the what we proposed regarding training and learning integration schemes beyond criterions that are kind of adapted for linear ODEs, and moving to the time integration and the derivation of integration schemes that are adapted for the integration of nonlinear ODEs and for the data-driven identification of nonlinear differential equations. I'll then present some numerical experiments, and I will end up with a conclusion and some perspectives. And please do not hesitate to stop me if you want me to explain something or want to discuss some point. We don't not have to wait until the end of the presentation. Okay, so when we are talking about numerical integration, we are most of the time given some differential equation. And so can you see the cursor? Yes, right. I will assume that you can see the cursor.
Yes, we can. Yes, we can see it.
Thank you. Thank you. Yeah. So we are talking about numerical integration. We are most of the time given a differential equation, something like this, with a given initial condition, and we want to kind of compute the solution of this differential equation. Now, the issue is the fact that most of the time we cannot compute this solution analytically because integrals are extremely difficult to be computed. And we are kind of obliged to use an algorithm from numerical integration. So this phi d here that approximates the true solution or the analytical solution of this differential equation. Now the issue is how to make sure that this this numerical integration, this algorithm here, is correctly approximating the true solution that we cannot compute analytically. So we do not have the true solution, but we still want our algorithm, our numerical algorithm, to approximate this true solution. And the answer is written in precision and stability criteria of numerical integration schemes. So quickly about precision of numerical integration, it is mainly evaluated using what we call the truncation error. So truncation error is simply the error that is intrinsic to an integration scheme when, so every integration scheme has its own truncation error built on some kind of differential equation. And when integrating a single integration time step. So given a time discretization integration time step, what is the error done by the integration scheme given a perfect initial condition? This is a truncation error. So it's it can be written as simply the difference between the true solution at t+1 and the integration scheme output at t+1 given a perfect initial condition. So from here we can write the true solution as a Taylor expansion of the true solution from t to t+1, and the integration at t+1 as the integration scheme given a perfect initial condition. So this is an error here. Extremely sorry for that. It's not z hat, it's simply z, because we are assuming a perfect initial condition. Otherwise, it will not be a truncation error because the initial condition also have an error. Anyway, so when computing this difference, and now by assuming, and most of the time that's what we do in state-of-the-art literature, so we assume that this function here is a linear differential equation, and assuming also that phi, and so this thing here, the thing that is linked to a Taylor truncation of the true solution of a linear equation, is a p-order integration scheme, which means that these things here go to an order p. we can derive an equation for this truncation error that can be written as a function of the time scale of the system, the integration time step, the order, and the state of the system. So here it's assuming that differential equation is linear. It's extremely important. So we can actually discuss this truncation error as a function of the order of the integration scheme, and it's not conclusions are not as easy to make as we want them to be, right? Because, for example, for values of lambda h, so the time scale, and similarly the integration time step, when this value is small enough, high order integration schemes that can be seen in the zoom here, but high order integration scheme for small enough values of lambda h, high order integration scheme tend to have a much lower truncation error than low order ones, right? And this is kind of expected because high order integration schemes match the true Taylor expansion longer. Now the issue is when we above a certain threshold for values of lambda h, so for values of time scale and similarly time step, the integration time step, high order integration schemes actually perform worse than low order ones, and this is mainly due to the lambda h to the power of p+1 here, which induces lots of errors. And from here, if we are kind of constrained by the integration time step that we want to use in some integration related problem, we are not necessarily sure that high order integration scheme will achieve better than low order integration schemes, because we have this issue of when lambda h is above a certain threshold, low order integration schemes are better. So this graphic is just to show that high order integration schemes are not necessarily better than low order ones. Actually, they are not when considering stability criteria, but we will talk about this in a slide after this. Anyway, but moving back to this equation here, we'll remind also that this equation was computed for linear differential equations. And what happened in the nonlinear case, because most of the time we are more interested in nonlinear, at least the equations we are interested in are nonlinear, and what are the precision properties of integration scheme when considering nonlinear equation? And the answer is we mainly do not know, because what people do, in at least as far as I know, is some linearization of nonlinear equations and achieving the same kind of study of on a linearization of nonlinear dynamical system. So this is to say that we have little to no knowledge regarding the performance of such integration scheme, the integration of nonlinear differential equation. Okay, so the second thing I want to kind of quickly introduce to you, because before going to what we proposed, is stability of numerical integration. And the reason we want to care about stability is simply because the truncation errors, or the mean to evaluate precision, is simply computed for perfect initial condition. And in practice, we do not have perfect initial conditions, right? We only have a single perfect initial conditions, and throughout the integration, we have the errors from one step to another actually propagates by numerical integration scheme, and they may become unbounded, leading to instability of the integration scheme. So stability analysis simply makes sure that the integration scheme does not blow up, so it does not go to infinity regardless of its precision properties. And one of the main kind of criteria that are used to assess about the stability of a given integration scheme are also built on linear differential equations. So assuming that we have this linear differential equation here, and since our real lambda is inferior or equal to 0, this means that this differential equations actually is bounded or goes to 0. So the solution of this equation given integration scheme can be written in this form, because this is a linear equation. So we can factorize the equation to something like this. And with RD here is what we call the stability function of the integration scheme, and it's function of lambda h. And the numerical solution is stable whenever the stability function for values of lambda h is inferior to 1. This will mean that this numerical integration scheme actually is bounded when RD is equal to 1, which corresponds to real lambda equal to 0. And when real lambda is negative, RD is negative, and it also goes to 0. So it does not diverge, and the numerical integration scheme is stable. This is an example of stability region for the Runge-Kutta-4 scheme. And we can see that there is several values of lambda h for which the numerical integration scheme is stable. Now, the issue is that this is also computed for linear equation, and what happens when considering nonlinear differential equations, right? And usually what we do is also we compute linearizations around some point in the phase space. And from this linearization, we compute eigenvalues, and we see the largest eigenvalues, and we match it with the smallest integration time step in order to guarantee that we are in this region here. This is tremendous amount of work, so computing linearizations and stuff like that, especially for high dimensional systems. So actually, we do not do that in practice. we use black boxes like adaptive steps as solvers and stuff like that, but we'll talk about it later. Okay, so to wrap up kind of this session about criteria of precision stability of numerical integration, we can say that they are mainly designed most of the time for linear differential equations, and we had this concern about how to guarantee their applications or how to derive something that is adapted from the integration of nonlinear equations and something beyond simple linearizations of nonlinear differential equations. And another question that we asked ourselves is how about what about identification applications for which, for example, we have a sequence of observations that we know evolve nonlinearly because they do not resemble to a linear dynamic. And we aim to identify some kind of a differential equation that reflects the variability of these observations. So from here, we need to choose an integration scheme and which integration scheme to use and which corresponds to which time step. And this lot of questions that we kind of we were stuck to when thinking with classical kind of choosing integration scheme point of view. So what we propose from here is simply to learn integration schemes from application-oriented cost. So such framework will allow for integration schemes to be adapted for the integration and identification of nonlinear equations. And how do we do that? Is simply by parameterizing a Q stages Runge-Kutta scheme on a framework that on a differentiable framework. So the parameters of the Q stages Runge-Kutta scheme can be trained from an application-oriented cost. And so a little bit more into details. So what we do is simply we start by stating integration-related problem using a trainable Runge-Kutta scheme with a predefined number of stages. So, for example, when considering the integration of nonlinear differential equation, we write this nonlinear differential equation in a differentiable framework, as well as we write this nonlinear equation in the differentiable framework, as well as the trainable Runge-Kutta Q stages scheme in the differentiable framework, as well as so we write time integration using this Runge-Kutta scheme. We then define the parameters that need optimization. So there are necessarily the parameters of the integration scheme. We can as well put some extra parameters, for example, unknown parameterizations for the differential equation, or a data-driven model like a neural network when considering identification of the dynamics, not necessarily identification and stuff like that. In the third step, we define a list function that is related to the performance that we want to optimize. For example, we can consider integration root mean square error, identification root mean square error, as long as, or as well as, for example, stability constraints or order constraints, classical ones on linear equations. And we finally just do optimization using gradient descent. And this is kind of the workflow when considering the identification of nonlinear dynamics. So given some observations, some training sequence, we write in differentiable framework a neural network that is integrated through a Q stages Runge-Kutta scheme. We then optimize both the parameters of the Q stages Runge-Kutta scheme as well as the parameters of the neural network to minimize the forecast of the observations. And we end up with a trained integration scheme, a trained differential equation or neural network that mimics a differential equation, and that can be used bothly to do, for example, data-driven model prediction or simulation of the observations. Okay. So the first experiment that we want to achieve using this framework is try to match state-of-the-art literature in the derivation of the Runge-Kutta schemes. In some of case studies, we did not treat all of the case studies, but one case study that we treated is derivation of stability constrained Runge-Kutta schemes, and this is one of the most kind of techniques used in literature to derive what we call optimal stability polynomials for Runge-Kutta schemes. And how do we do that? Is simply we assume a linear differential equation. We write the polynomial form of the polynomial form of the integration scheme, of the Runge-Kutta integration scheme, written as our integration is equal to a stability function times the integration at t minus 1. This is an error here. Another error, sorry for that, but it's z hat t plus 1 is equal to this function here times z hat t. Okay, so the objective of stability constrained Runge-Kutta scheme is simply to find schemes that are stable for the largest values of lambda h. So for largest values of lambda h, we will have still the stability functions that is but inferior or equal to 1 in absolute value. Okay, so yeah, we can, two of the main treated case studies in the literature kind of treat cases where the eigenvalues lambda here are real. So this is what we call real axis inclusion, or cases where the eigenvalue here lambda is purely imaginary, and this is what we call imaginary axis inclusion. It corresponds from the numerical system point of view to the simulation of diffusion or advection processes depending on the value or nature of the lambda. Anyway, so we tried our framework, so the Q stages Runge-Kutta scheme with different number of stages ranging from 4 to 10, I think, and we kind of get this beautiful results regarding stability region, and it actually matches the state-of-the-art techniques, optimal stability polynomial optimization, that do not necessarily use automatic differentiation, stuff like that. They define their own basis for the polynomial RED and their own optimization function to get something like this. Our framework is able to get similar results without any specialization. Okay, but we are mainly more interested in the integration identification of, or in treating nonlinear ODEs, right? So the second case study is we took a nonlinear differential equation, so the Lorentz 63 system, and we trained a 4-stage Runge-Kutta scheme to integrate Lorentz 63 trajectories that are sampled at point 1, 15, 16, 17, 18, and 19. So when compared to classical Runge-Kutta 4, so a scheme that is optimized to reach a 4th order truncation of its Taylor expansion in the truncation error, so it has nothing to do with some nonlinear ODE or stuff like that. What happens is for integration time step equal 0.1, both trained scheme and the Runge-Kutta 4 schemes are able to integrate chaotic trajectories from the Lorentz 63 equation. Now, when considering integration time step of 0.15 up to 0.17, there is only the trained Runge-Kutta 4 that is able to simulate chaotic trajectories from the Lorentz equation, and the Runge-Kutta 4 either goes to infinity or gets stuck at an equilibrium point. Now, for larger values of the integration time steps, both the integration scheme actually diverge to infinity. And this
Said,
Yeah.
On this, could you be more specific on the criterion you consider?
Yeah, the criterion is given. Yeah, the criterion. Thank you. The criterion is simply given initial condition that is in the bassin d'attraction of the chaotic solution of Lorentz. So not we are not in the equilibrium point of Lorentz, stuff like that. So we are as given initial condition, we are supposed to have a chaotic solution. So we are evaluating either the integration scheme that is trained and the range Kuta4 schemes are given chaotic solutions from these initial conditions. So everything that is not chaotic solution is rejected, and it's written here as a cross. It means that the integration scheme does not work.
Numerically speaking?
Numerically speaking, it's either when there is an x here, it means that the integration scheme either diverges to infinity or goes to an equilibrium point.
Okay.
When there is when it's not a cross, it means that it generates chaotic trajectories. Okay.
Thanks.
You're welcome. Thank you for the question. Okay. Yeah, an interesting experiment now is to plot the stability regions of the those trained Rengi-Kuta schemes for various values of the integration time step, and comparing it to G here. This is the stability region of the classical Rengi-Kuta4. And what actually happens is, as the integration time step increases from 0.1 to 0.19, the stability region of the trained Rengi-Kuta schemes increase toward the imaginary axis, which emphasizes that the Lorentz 63 equation is mainly dominated by an advection process, not necessarily diffusion one. Those requirements are actually identified by the algorithm automatically to correctly integrate the Lorentz 63 equation. And what happens in the 18 and 19 integration time steps? It's actually the ADRK framework actually tried to increase more the stability region toward the imaginary axis, but it's catched by the feasibility constraints. So the consistency constraints of the range Kuta, which makes it at least first order. So it cannot be larger with 4 stages than this stability region. And in order to have a large stability region, we need to increase the number of stages. And this is why it does not work where 18 and 19 here. Sorry. Yeah, okay. The second case study now is regarding the identification of nonlinear dynamics using this framework. So also with the Lorentz 63 system, now what we want to train is an 11 stages Rengi-Kuta scheme that is trained jointly with a neural network to generate Lorentz 63 data coming from data sampled at 0.2, 0.3, and 0.4. And when comparing the short-term forecast of the proposed framework to classical state-of-the-art technique, what happens is, when considering sparse regression technique, which is simply SINDI, right? We compute an augmented state vector based on polynomial regression and based on polynomial representation, and then we compute the best linear fit of this augmented representation, and we kind of threshold the smallest term, the terms of the linear regression. And can be roughly described like this. It's a little bit more complicated, but can be roughly described like this. But what happens is SINDI does not work at all when considering h equal this and time samplings of the observations, simply because it needs an estimate of the derivatives of the time series. And when using these sparse observations that are poorly sampled in time like this, a good estimation of the derivatives becomes impossible, which makes this algorithm do not work. Now, when comparing to so using a neural network model similar to what we used in ADRK and Dokriwit here, but with fixed step size solver that are Euler and Rengi-Kuta4, the identification also do not work. It's simply due to the fact that when using these kind of classical integration schemes, truncation error is extremely high, which makes the error that is due to the integration, or no, to the identification, kind of lost in the truncation error, which makes the identifiability impossible. I mean, a simple way to kind of picture this is to say that, for example, if we use the true dynamical model and try to integrate it using Euler and Redkuta at this time step, it will not work. So of course, it will not work in identification perspective. Okay, so the third kind of family or type of techniques that we compare to is trying to identify data-driven models that forecast the dynamics of the observations that uses an adaptive step size solver, such as Dopriwit here. And when using adaptive step size solver, what we did here was actually using the technique of the neural ODE papers that uses the adjoint sensitivity methods to compute the gradients of the forward pass using an augmented reversed in-time differential equation. And when using this, actually, we have extremely small memory cost of the adaptive step size solver when using the backward. We can identify at h.2 and h equal 0.3, but we cannot identify the dynamic at h equal 0.4. And this is mainly due, from my point of view, to the fact that integrating a backward differential equation in time is extremely unstable and a poorly conditioned problem, because all of the eigenvalues of the system will have a switch in their signs. So when they are stable, they become unstable, and each small perturbation will get exponentially increased, which makes the identification impossible when for large values of the integration time step. Okay, so this is a visual comparison of the attractors simulated from our framework, so the ODEs here, and the neural ODE with the adjoint sensitivity method. And what happened is, similarly to what we showed in the short-term forecast table, is the fact that neural ODE cannot simulate dynamics at h equal 0.4. So what we did from here is we did not use the adjoint sensitivity method to compute the gradients in training phase, but we did kind of a simple residual integration tactic where we store all of the evaluations of the adaptive step size solver in order to do the backward pass. And when we do this in the training, we can actually properly identify lower 63 dynamics at h equal 0.4. But now the issue is when we compare the number of evaluations of the approximate functions of f theta from the proposed framework to the neural ODE. So it's the red thing in here, given all this red. This number of evaluations simply given in initial condition here in the trajectory. How much the neural network model is evaluated, or is evaluated in order to compute the next time step prediction. And when for the proposed framework, it's simply the number of stages, so it's 11. Regardless of the initial condition. Now, for the neural ODE model, it's an adaptive step size solver. So, given an initial condition, it will divide the given time step as much as needed in order to guarantee some performance criteria, which means that for every division of the time step, there is an evaluation of the function f theta, at least a single evaluation. Now, assuming that the integration algorithm is Euler. But it's Dopriwit, so they use up to 8 order or 11 stages So it will be bounded from this number times 1 to this number times 80. But this is lower bound estimate of the number of evaluations, and it goes from kind of 16, I remember, to more than 1,000 evaluations of the function f theta, which is extremely high, especially if we consider applications for other systems that are not necessarily three-dimensional. Okay. We also aimed at evaluating the performances of the trained Runge-Kutta schemes, trained Runge-Kutta schemes on this identification case study. And what we discovered was kind of a little bit similar to what we saw in the integration case study, where when we increase the time sampling of the observations, the problem becomes more harder, and the integration schemes have a larger stability region in order to guarantee identifiability of the dynamics. This is in stability region figure. And you see that, for example, when we move from H1, which is equal to 0.2, to H3, which is equal to 0.4, the integrated stability region increases. And this is with the same number of stages. All of them have 11 stages. And order estimate is simply it's an evaluation of the order of the trained integration scheme. And what happens here is when moving from H1, which is equal to 0.2, to H2, which is equal to 0.3, we have actually the order of the integration scheme that increases from kind of 6 here, if we consider that this is an good error for the order, from 6 here to kind of 8. So the lower the bar is, the higher the order is, right? And when we move from H2, which is equal to 0.3, to H3, which is equal to 0.4, we have actually a decrease in the order. So the order decreases from 8 for the orange bar here to approximately 6 or 5 for the green ring, for the green scheme here, which corresponds to the blue stability region here, the large stability region. And what happens here, I think, is linked to the figure I showed earlier regarding the truncation error and the truncation error of a high order integration scheme, and how it increases above a certain integration threshold. And if we assume that this integration threshold here is H3, which is equal to 0.4, we have a decrease in the order in order to lower the truncation error in order to guarantee identifiability. Okay, so now moving to some conclusions and some perspectives. I think that the proposed framework allows for learning adapted integration schemes for the integration identification of nonlinear ODEs, and it also allows to have similar results in state-of-the-art derivation of, for example, stability constraint integration schemes. Now, regarding the perspectives, I started kind of thinking about the application of such formulation for the identification of or integration of stiff differential equations. And this is not necessarily from an implementation point of view, or because in order to integrate or identify stiff phenomena or differential equations, we simply need to use implicit integration schemes, because they do have a much larger stability region, which allows for acceptable step sizes. Now, the issue is, I think, more from an identification perspective, because stiff phenomena have this very quick intermittent behavior, and how to make sure that this very quick behavior, when compared to all the other time scales of the systems, is not treated as noise from a training perspective. I'm kind of trying to think about this and how to deal with it in order to identify stiff differential equation. Now, another issue that we actually started investigating is is there any issue when treating higher dimensional system? And what I actually tried to start doing, what I started doing is to apply this framework in the time integration of partial differential equations, so with much higher dimension than, for example, what I showed in here, Lorentz and linear equations, and see, for example, on different types of differential equations or partial differential equations, do the integration scheme adapt to this or this category of partial differential equation, stuff like that. Okay, so this was my presentation. Thank you, and I will be happy to discuss whatever you want to discuss.